14.54 has two balls, A and B. Mass of A is 2 kilograms, mass of B is 1 kilogram. They're attached by a string. The balls are rotating about the center mass, and the center mass has a velocity v naught in this direction. We're given information like x naught bar is 0 and y naught bar is 1.89 meters. We're told that v sub A right here, after the balls break loose from each other, v sub A is traveling vertically at 5 meters per second in the J. We're told the A value right here of 2.56 meters. We're given the value of B as 7.2 meters per second I and minus 4.6 meters per second J, and that the B value right here is 7.48. What we're asked to find in this problem is what is the initial velocity of the center of mass, and then what is the length of this line right here, and what is the angular velocity that A and B have about the center of mass position. So the A part is to find the V naught bar. We're going to have conservation of momentum in the x direction and conservation of momentum in the y direction. For the x direction, we'll start off by writing m, total mass of the system, so V naught x bar equal to ma VAX plus mb VBX. Remembering that m is equal to ma plus mb. And from this, VAX you can see right here is 0 afterwards, so this will lend us a value for V naught x, because we know VBX is 7.2 times the 1 kilogram mass, and we divide that by m, which is 3 kilograms, and we'll get 7.2 divided by 3, which is 2.4 meters per second. So that's the x component of the center mass velocity. We look at the conservation of momentum in the y direction. We'll have m, total m, v naught y bar equal to ma VAY plus mb VBY. And remember, VAY is a plus 5 and VBY is a minus 4.6. So you stick your numbers in this equation, you get 1.8 meters per second for V naught bar in the y direction. So to get the total V naught, it's going to be the x component, 2.4 meters per second I, plus the y component, which is 1.8 meters per second J. And this gives you 3 meters per second at 36.9 degrees. For the B part, we're going to find the length L of the cord, and to do that we're going to use conservation of energy. We'll start off by writing that we have an energy of 1/2 m total mass of the system times V naught bar squared, plus then the energy that you have with respect to the center mass of 1/2 ma, the velocity of A with respect to g squared, plus 1/2 mb, the velocity of B with respect to g squared. And that's got to be equal to the energy that you have afterwards, which is 1/2 ma VA squared plus 1/2 mb squared. And you get rid of the halves all the way across, substitute in the masses, and you end up with this equation right here of 3 V naught squared plus 2, and then we'll get to these two terms here in just a minute. And then you have 2 VA squared plus VB squared. Again, the 2 is coming from the fact this is 2 kilograms, that's just 1 kilogram. Now let's look at A and B line right here, and let the total length be LA plus LB right here. And we're going to calculate the center mass position located right there by doing the total mass times the length LB. That's the position right here. And we're going to measure it with respect to B, and that's going to be MA times the total length L right here, plus MB times the 0 position for it. And so when you solve for LB out of this, you'll get that it is 2/3 L, which implies that LA is 1/3 L. So we go back into this equation right here, and the velocity of A with respect to G is going to be LA times omega, and then quantity squared, and then the velocity of B with respect to G is going to be LB times omega, and that quantity squared. And so when you start squaring out these terms, you'll end up with this equation right here, 3 V naught bar squared plus 2/9 L squared omega squared plus 4/9 L squared omega squared equal to 2 VA squared plus VB squared. Now, the next thing we're going to look at, because right now we got L and omega both are unknowns in this energy expression, we're going to look at the angular momentum about point O. And point O is this point right here. And so the angular momentum initially is going to be equal to the angular momentum about point G plus the position of the center mass R bar basically crossed into MV bar. This right here is all known. All of this turns out to be in the K direction. So let's go to the next page for a continuation of this problem. Again, we repeat this equation from above. Now we're going to look at the initial angular momentum, or excuse me, the final angular momentum is going to be R sub A slash O. It's going to be the momentum that A is carrying right here, which is MA, VA at A distance, and it's a counterclockwise angular momentum. So, and then B is going to carry, the X part is going to carry no angular momentum about O, but the Y part is going to carry a clockwise angular momentum. As we plug this back into our equation over here, then we'll have R crossed into MA, MV for A would be an A, MA, VA. For R crossed into MVB or MBVB, we're going to pull out the BY part and B and MB. And you'll notice that VBY is going to be a negative number, and that's going to cause this to produce a clockwise moment, as we know that it does. For the angular momentum H sub G here, we have that the RA is going to be an LA, and then the EMA, and then the VA is going to be an LA omega. So you're going to end up with MA LA squared omega. And the same thing for B, and both of those are counterclockwise, and so that's why positive numbers are placed here. And then when you do your R sub G slash O crossed into M V naught bar, you're going to get the total M right here. You're going to get V naught Y, Y naught bar. And then the X part of that velocity is the only one producing a moment, and it's going to be a negative angular momentum associated with that. So when you plug your masses in and get rid of the units, you'll end up with 2A VA plus B MV VBY. And then over here, you'll get a 2/9 L squared omega, a 4/9 L squared omega, and this right here will be a -3 Y naught bar, V naught X bar. These two will combine to become 2/3 L squared omega, -3 Y naught bar, V naught X bar. And I'm going to do a little thing unusual here. I'm going to actually solve for L squared omega out of this equation. And when you do, you get all this right here, which is known. It turns out to be 7.2 meters squared per second. I'm going to plug this back into 1, because if you go back and look at 1, the unknown that you have in here is L squared omega squared. But I have, if I put the L squared and one of the omegas together, I can plug in this number right here. And in doing so, I'll end up with an equation that looks like this, with omega is the only unknown, and when you solve for omega, you get 20 radians per second, which leads you to, once you know omega right here, you can solve for L and get 0.6 meters for L. And of course, the C answer is omega equal 20 radians per second that we've already calculated.